Hello again. Thank you all for watching. Today's topic is rational exponents. Remember that rational numbers are the ratio of integers. That means we need to understand what negative exponents mean, and we have to introduce the quotient rule. And in the context of all this, we'll revisit complex fractions. As always, reading your book and the examples in your book is strongly recommended, and start and stop this video to make sure that you're understanding the material. So, a negative exponent is defined this way: for any non-zero number and in an integer a to the minus n is equal to 1 over a to the n. One mistake students sometimes make is to think that the negative exponent doesn't indicate a reciprocal but a sign change in the expression. Be careful not to make this mistake. So here is example 1 dealing with the definition of the negative exponent. You're to write each expression without negative exponents. Your final answer should not have negative exponents in it, and evaluate if possible. Assume all variables represent non-zero real numbers. Let's see how you do. Here are the answers. Probably the most significant one is here. If minus 1 is the exponent, the base is 5, so the minus stays with the final answer. We also have a quotient rule. If we have a to the m over a to the n, it's equal to a to the m minus n. So when dividing powers of like bases, keep the same base and subtract the exponent of the denominator from the exponent of the numerator. And then you work to make sure you don't have a negative exponent in your answer. Here's classroom example 2. Using that quotient rule, simplify each expression and assume all variables represent non-zero real numbers, so we have no problems with 0 in the denominator. So let's see how you do. Here are the answers I got simplified. Please ask questions if you didn't get any of these correct. Using all those rules of exponents, then, we're to simplify each expression and write our answer as always without negative exponents. And again, all variables represent non-zero real numbers. Let's see how you do. These are the answers I got. We're now going to extend the definition to define what it means to be a to the 1 over n. And a to the 1 over n is a number whose nth power is a. And if it's an even positive integer, then that is the positive real number whose nth power is a. If it's odd, is an odd positive integer, and a is any non-zero real number, then a to the 1 over n is the positive or negative real number whose nth power is a. And 0 to the 1 over n is equal to 0. You see, it makes a difference if it is even or odd. So here is using the definition of a to the 1 over n. You're to evaluate each of these expressions, and this was a typo. Let's see how you do. Here we see that there is no number that we can raise to the 6th power and get a negative number, and no real number, so the answer to that is not real. Now we go full circle and we talk about the expression a raised to the fraction m over n, and that is a to the 1 over n that we've just studied, and then that is raised to the mth power. So that's how we define this, and classroom example 5 deals with this. So use this to rewrite each expression and fully simplify. Let's see how you do. And here we see you cannot take a square root of a minus 100, so that answer is not real. Here's a summary of the rules for all the exponents that we've studied now, including the negative exponents. And here R and S represent rational numbers, so this is the rules that we follow for all of those. You want to commit these to memory. Classroom example 6 uses these rules of exponent to simplify each expression. As always, any variables are positive real numbers, so we don't have to worry about zero in the denominator. Let's see how you do. Here are the answers I got, and you should get answers like these. Example 7, there was a typo here. Example 7, we wanted to factor out the least power of the variable or variable expression, and again assume that all variables represent positive real numbers. This is something that actually happens often in a calculus course after you've taken some derivatives. Let's see how you do. These are the answers that I got. Again, find out what you did wrong if you get different answers than these. And finally, we apply this principle to complex fractions where we have rational expressions in the numerator and denominator. We're to simplify this. Closing. Remember, time is precious. Each day must count. Doing the math will make you strong. Take care, and I'll see you in class.